question, we need to find the number of real ordered pairs x comma y for which this equation holds, right? Okay. So for simplicity, let's substitute A and B. A as x square plus y and B as x plus y square, so that we don't have to write these long terms again and again. So what we get ultimately is 16a plus 16b is equal to 1. Now whenever we see exponents, an addition on one side and a constant on the other side, we somehow try to think that how do we make sense of it. So we try to use AMGM inequality. Let's see if we can get anything out of that. Right now we are just experimenting, applying all the things we know. So a plus b is greater than 2 root of ab. Then we'll get this thing. 16a plus 16b is always greater than this thing. But we still have to find a and b, right? So our problem is still not over yet. But now we know that 16a, 16 raised to the power a and 16 raised to the power b are always greater than 0. So this thing we already know and it is pretty simple, right? So we'll see if negative values are possible or not. Okay, so if both a and b are less than 0, negative values for a and b, right? Remember, for a and b. So now if both a and b are less than 0, then of course the powers, whatever we'll apply, 16 raised to power a will be bound to be less than 0, right? So if both of them are less than 1, then their addition is also bound to be less than 2. But now somebody can say that why we are directly saying that is less than 1. How could you say that? So to prove that, let's focus on this side. So let's suppose that one term is a. Now one term is 1. And for that to be 1, a has to be 0. And the other term has to be 0 to be equal to, so that RHS can be 1. But b, but if this has to be 0, there is no b possible, right? Because it is 16 raised to power b and it always has to be greater than 0, right? It cannot be negative or it cannot be 0. That means that neither a nor b can be equal to 0. And of course, they cannot be greater than 0 either. Because if we take, because then RHS won't be satisfied. So they both are bound to be less than 0. Neither one of them can be greater than that, right? We have to deal with decimals here. So that on right side, because we cannot, because both of them are positive. So that is pretty obvious thing which we found right here. Okay. Now we are viewing the condition from a different lens. We are still experimenting. Let's see. Let's say that P is 16 raised to power A and Q is 16 raised to power P, where P and Q are greater than 0, of course. Given P plus Q is equal to 1, this thing is already given to us. Now note that A and B are not independent. They are not, because A is x square plus y and B is y square plus x, right? So let's try for the condition x is equal to y. So when we view this function and we are required to find the ordered pairs, or we are required to find basically the values of x and y for which this thing satisfies. So what first things comes in our mind, that let's try making both of them equal. Okay. So this is the thing which came to our mind and we solved for that. Both of a and b became equal. Then we came to this part, 2 into 16 raised to power a is 1. Then we further solved it, and finally we got a as minus 1 by 4. But we don't need a as the final value. We still need to solve for x and y. So we'll substitute the value of a to be x square plus x and equate it with minus 1 by 4, right? Then we'll put this on the left side and then we'll see it is a perfect square and we are getting x as minus 1 by 2. And since x and y were equal, then y is also minus 1 by 2. Hooray, we got a solution, right? But we still need to know if other possible pairs of x and y are possible. This is one thing which we assumed, and we were lucky enough to get a real root. But interesting thing is to note exponents, right? Can you see these exponents? So for simplicity, let us think this is a gx function, right? And this is hx function. So can you see they both are symmetric in x and y? If we substitute y in gx and similar thing in hx, right? Gx1, sorry, not it. We, since it is in two variables, we have to include two variables. So we can see that even though we substitute, so we can see that gxy on switching x and y is equal to hxy, right? That means they both are symmetrical in x and y. So now the interesting part comes, which is you need to remember, right? So whenever a problem is symmetric in x and y, the trick is to compare two expressions by subtracting them.